Hi there, look today at exercise 7D. Now today we're looking at what are called cumulative distribution functions. Now in the past we've always seen what are called probability distribution functions, usually written PDF, and usually written with this lowercase f of x. But today we're looking at what are called cumulative distribution functions, which are usually written with a capital F, just to distinguish between the two. And I suppose it's probably easiest just to remind you what we saw at GCSE. The start from GCSE would say, well, these are the lengths, I don't know, of variety of different vegetables, and in centimetres, and these were the number of vegetables which were of that particular size. And you should recall that you at GCSE got asked to say, well, up to now we've got none, and here we've got 2. But now these are cumulative frequencies, so if we get 4 more between 20 and 30, we've got 6 so far. And this, well, you might have been told this is like a running total or running score or something. So now I've got 10 more, so this is 16. I've got 17 more, so that sounds like 33. 11 more, so that's 44. And looks like I had 47 vegetables in total. So this is what we meant by cumulative frequency tables at GCSE. And I suppose the idea here is the same idea, that what we're trying to do is add up the probabilities as we go along. Let's put some better numbers on there. I don't like that. That goes from 50, I'm going to say, up to 100. That looks like a better scale now. And so what I'm trying to highlight to you here is, now the scale looks a bit dodgy, so that's, I'm going to say, is 100. And the reason why I'm saying that's 100 is because this is meant to represent all of the total. Sorry, this one is meant to represent the total of the probability densities as we go along. So if we kind of add up that, and we add up that, and we add up that, at an equivalent point we would get to the same thing. So I reckon it starts to change about there. So I don't like my scale, but I reckon that's at about 50. And you'll notice it goes up, gets steeper and steeper and steeper, and then at about this point it starts to tail off. And it starts to tail off until eventually it's got to its maximum. Now that corresponds to adding up all these, and eventually when we get to this point we've kind of reached the peak of the maximum of the PDFs, and therefore the amount we from now on are starting to add on are getting smaller and smaller and smaller, until by the time we get to 100 we've got nothing left to add on. And that's why beyond that it doesn't go any higher. And we'll talk about this properly now, but just notice this is a cumulative distribution function, and it's written with a capital F of x. So a few rules for these cumulative distribution functions. The first one is that in order to get it, we basically integrate the f of x's. So we get the f of x and we integrate it. Now from minus infinity up to some value x, which seems a bit weird. The x just allows it to still be a formula. And the minus infinity isn't necessarily minus infinity, it depends on where it starts. It's saying from wherever you start up to some value has this formula. And this integration is really saying add up all those areas that we had in the last graph, the PDF graph. And because this is integration, we can also go backwards. If we start with the f of x, we can find little f of x, the PDF, by differentiating the big one, the CDF. So these are formulas which we are meant to understand and use. We've got the answers come up straight away here, which might help, it might not. Let's just see. Find the cumulative distribution function of a continuous random variable x, which is this PDF. So my function, and if I was to draw this, it goes from 0 up to log 2. I think I saw this graph on the last one we did. And it goes from there. If I put 0 into e to the x, it's 1. And if I put log 2 into this, it's e to the log 2, which is 2. So that's my f of x graph. Anywhere else, not in between these two values, it is 0. So technically it's there, then it jumps up to there, and then it comes down again over here. But this is my graph. Okay. And it wants the cumulative distribution function. Oh, we saw a formula just now. It said the CDF f of x is the integral, and it said from minus infinity. Well, I don't have to go to minus infinity. I can start at 0 and go up to x of e to the x dx. Now, if I integrate this, if you integrate e to the x, you still get e to the x. So really, this is e to the x between 0 and x. Now, if I put x into this, I get e to the x. If I put 0 into this, I get 1. So there's my formula, e to the x minus 1. Now, that bit will give me this bit here, the e to the x minus 1 bit. But you'll notice there's also, we are expected to try to display this in a way which links us to the way we got these originally, i.e. it's between these two values it's this, but anywhere else it's 0. So one thing I can say about the CDF, well, let's think about the e to the x graph minus 1 by the way. E to the x at value of 0. If I put 0 in it, I get 1. So 1 minus 1 is 0. So at 0, it is 0. And if I put log 2 into that, log 2, if I put e to the log 2, I get 1. Minus 1 is, sorry, e to the log 2 minus 1 is 2 minus 1, which is 1. And so one of the facts that we have with these graphs, and I think this graph basically just does that, is it stops when it gets to 1. The maximum f of x graph, a PDF, a CDF graph can ever be is 1. It will never go above it. So there you go, that's it at 1, and it's 0 anywhere else. So, well, that's rubbish. It's there, that's really what I meant to say. It's 0 before it, but after it, it's already at 1. So if I carry on going, it's still at 1. So that's what this is meant to say. This is saying it starts up at 0, it ends up at 1, and these are just the values for which it takes place. So up to 0, it's nothing. Between 0 and log 2, it follows the formula which we found here, and beyond that point, it is at its maximum forever and ever and ever. So that's at 1. So this is the answer, and that might seem quite easy. I suppose it is until you see a harder one. Next example. Now this example is actually the other way around. This is saying f of x is this. So notice what I said before. I can find the PDF by differentiating this. So if I differentiate x squared, hopefully you will agree that is 2x. So this tells me, again, that the PDF, therefore f of x, now, I don't know why I did that, it's one of those brackets, and it will be 2x between, well, it says between 0 and 1. Anywhere else, 0. Because it was 0 before, and after this value of 1, it doesn't get any higher, so it must be 0 after that. The graph of this basically does that, doesn't it? And between 0 and 1, that's what it looks like. Find the lower quartile of x. Well, to find the lower quartile, well, quite a nice thing about f of x, I can say that f of x equals a half. A quartile, not a median. So I can just say x squared equals a quarter, and therefore x is the square root of a quarter, and the x value where that happens is a half. So I reckon half, a quarter of this area, of the total area, is being used, if you like. And there it is. So, and notice my answer here, will allow for my dodgy start, that's actually a better answer than this. But you can get away with doing it like that as long as you clear what you've said. I'm going to do another example for you. So here's another one. We've got a cumulative distribution function of continuous random variable x as a probability density function of that. Now you'll notice it actually says k, so we don't even know what k is. Our very first job is to find k. And we've done these a few times now. The way we do that is to say the probability is 1. And we get the probability by just integrating f of x dx between what two values? It's 0 and 1. So if I integrate between 0 and 1 of my function, which is kx Now if I multiply it out, I get kx minus kx squared dx. I therefore get k add a power divided by the power kx squared over 2 minus kx cubed over 3. And it tells me to chuck in 0 and 1. So if I put 0 and 1 in, 1 goes k over 2, don't like that, k over 2. If I put the 1 into there, I get k over 3. And if I put 0 in, I actually get 0 out. So this is effectively k over a half minus a third of k is a sixth of k. So this is a sixth of k. And don't forget, the probability has got to equal 1. So this equals 1, so k equals a 6. Alright, so I've got my point now where I can now say that f of x, the CDF, remember this is the CDF, is the integral from the lowest point, which is 0, up to my highest point, well, highest point that I want to care about, which is x. And that is of now k I can write as 6. So 6x minus 6x squared dx. So if I integrate again, I get 6x squared over 2 minus 6x cubed over 3. Between 0 and 3. 0 and x, sorry, that's where 3 came from. So that cancels, that gets me 3x squared minus 2x cubed. And if nicely on this one, if I put 0 into this, I get 0 out. So my answer just becomes 3x squared. X replaces the x and gives me x. The x replaces the x and gives me x. So that's no different. But the 0 gives me 0, so that is my answer. And it just wanted the cumulative distribution function. So again, I've just got to make sure I write this properly. So f of x, you always start off with a nice curly bracket. It starts at 0, it ends in 1. And the thing that goes in between is the answer we just got. The values we started with are the values for the answer we've just got. This is for greater than it, and this is for x is less than it. That's what I think the answer should say, and it does. That's basically it. So this isn't hard at the moment. It comes harder when we get what are called piecewise functions, which basically means there's more than one bit. So you might have one expression for 0 to 1, and then between 1 and 2 you get another expression. And that does make it a little bit trickier. But for these, I think it's fairly straightforward. You're going to integrate to go from the PDF to the CDF, the little f of x to the big f of x. You're going to differentiate to go backwards to get the little f of x from the big f of x. And basically that's it. So there's some questions for you, exercise 7T, that I want you to do. Let me know if you have any problems. Thank you very much.